3 plants grow wild on 6 continents. One produces a blue so permanent it survived 3,500 years underground in a salt mine. One produces a red that dressed Roman legions and British armies for centuries without fading. One produces a yellow you can pull from a roadside ditch every September. None of them require a single synthetic chemical. The textile industry buried all 3, and by the end of this video, you will know how to dye your own fabric permanently using nothing but a kitchen pot, water, and weeds from your backyard. In 1993, a team of textile researchers entered one of the oldest mines in the world, the Hallstatt salt mine in Austria. Humans had been mining salt there since the Bronze Age. The tunnels go deep into the mountain. Buried inside those tunnels, preserved by the salt for thousands of years, the researchers found fragments of ancient cloth. These were not colorless scraps. They were dyed. Bright, vivid, unmistakable color walked into the fibers of fabric woven more than 3,000 years ago. The salt had done what no museum could. It froze the color in time. When the researchers analyzed the Bronze Age textiles, they found the blue dye compound indigotin present in a third of the samples. In the Iron Age textiles, the number jumped to nearly 60%. These were not decorative scraps. This was industrial-scale dyeing happening in Central Europe more than 1,000 years before the Roman Empire reached its peak. Half a world away and even further back in time, archaeologists working at Mohenjo-Daro in modern-day Pakistan recovered a piece of cotton from the ruins of the Indus Valley civilization. It dated to the 3rd millennium before the Common Era, 5,000 years old, and it was dyed red. The pigment came from a root. That same red pigment appeared in the tomb of Tutankhamun in Egypt. It appeared in the ruins of Pompeii. It appeared in the textile workshops of ancient Corinth. Different civilizations, separated by thousands of miles and thousands of years, using the same plant, getting the same red. Now consider what this means. Across the ancient world, 3 plants formed the foundation of every color humans could produce. One gave blue, one gave red, one gave yellow. From those 3 primaries, dyers in medieval Brussels, Byzantine Constantinople, and Mughal India mixed every shade the human eye can see. Green from blue over yellow, purple from blue over red, orange from red over yellow, brown and black from layering all 3. Every tapestry, every royal robe, every military uniform, every painted cloth that survives in any museum anywhere on Earth traces its color back to 3 plants growing in the ground. And somehow, in the space of a single generation, all 3 were erased from common knowledge. The year was 1856. A teenager named William Henry Perkin was working in a makeshift laboratory in his family home in East London. He was 18 years old. His professor at the Royal College of Chemistry had challenged him to synthesize quinine, the treatment for malaria. Perkin tried, and he failed. His experiment produced nothing useful, just a dark reddish-brown sludge at the bottom of his flask. But when he tried to clean the flask with alcohol, the sludge dissolved into a vivid purple liquid. He dipped a piece of silk into it. The silk turned a brilliant mauve, and it did not wash out. Perkin had not cured malaria. He had done something far more profitable. He had created the first synthetic dye from coal tar, the thick black waste product of gas production. An 18-year-old trying to cure disease accidentally launched a chemical revolution worth billions. Within 2 years, Perkin opened a factory. Within a decade, chemists across Europe were racing to synthesize every color in the spectrum from coal tar derivatives. The first target was the most valuable dye in agriculture, red. For centuries, the root of one plant had supplied the world with its most permanent, most sought-after red pigment. Farmers across France and the Netherlands grew vast fields of it. The roots took 2 years to mature. Harvest them, dry them, grind them into powder, and the pigment inside bonded to fabric so deeply that it survived centuries of washing and sunlight. The British government mandated this route for dyeing the uniforms of its soldiers. The famous red coats of the British Army came from this plant. Entire regional economies depended on its cultivation. Then, in 1868, two German chemists named Karl Graebe and Karl Liebermann, working at the chemical company BASF, figured out how to make the same red pigment from coal tar. Perkin in England discovered the same process independently. The two teams filed patents one day apart. BASF won by 24 hours. It did not matter who filed first. What mattered is what happened next. The synthetic version could be produced in a factory for a fraction of the cost. The price of the red dye dropped from $15 a pound to 55 cents a pound within a few years. 70,000 pounds of natural red dye had been produced annually across Europe. Within a decade, that number collapsed to almost nothing. Fields that had grown the red dye plant for generations were plowed under. Factories that processed the roots closed their doors. The French government tried to save the industry by passing a law requiring its army to use the natural dye for soldiers' trousers. It failed. The economics were impossible to fight. By the 1880s, centuries of agricultural tradition had been wiped out by a chemical that could be manufactured in a vat. The blue dye plant had already been through its own version of this destruction centuries earlier. In the 1500s, European merchants began importing tropical indigo from India. The blue was identical to what the European plant produced, but the tropical version was more concentrated. The European dye growers panicked. Laws were passed across France and Germany banning the imported dye. Authorities declared that the foreign product caused fabric to rot. In 1594 and again in 1603, European governments repeated the prohibition. In 1609, King Henry IV of France issued a royal edict threatening death to anyone caught using the imported blue dye. That is how much money was at stake. The bans eventually failed. Tropical indigo replaced the European plant, and then in the early 1900s, synthetic indigo replaced both. BASF, again. The last commercial harvest of the European blue dye plant happened in 1932 in Lincolnshire, England. After that, nothing. 3 plants. Thousands of years of use, exposed by economics, replaced by coal tar. Now look at what replaced them. The global textile dye industry produces roughly 700,000 tons of synthetic dye every year. About 100,000 different chemical formulations are on the market, and the waste is staggering. The World Bank estimates that 17 to 20% of all industrial water pollution on Earth comes from textile dyeing and finishing. 72 toxic chemicals have been identified in water contaminated solely by textile dye operations. 30 of those chemicals cannot be removed by any known treatment process. Every year, approximately 280,000 tons of dye waste pour directly into rivers, lakes, and coastal waters. The effluent contains heavy metals, lead, arsenic, chromium, cadmium, mercury. These are not trace amounts. These are industrial concentrations flowing into water systems that communities depend on for drinking and agriculture. The rivers downstream of textile factories in Dhaka, Tirupur, and Chayok run with color, literal color. You can see the dye in the water from satellite imagery. Children walk to school along canals that change from blue to red to green depending on what color the factory is running that week. 200 tons of water are consumed for every single ton of fabric produced. The synthetic dye market was valued at over $12 billion in 2024. $12 billion generating 700,000 tons of product, a significant percentage of which ends up as poison in public waterways. That is the system that replaced 3 plants growing in the ground. Now here is what the industry replaced: the blue. The plant is called woade. Its scientific name is Isatis tinctoria. It belongs to the cabbage family. It is a biennial, meaning it completes its life cycle in 2 years. It grows wild across Europe, Central Asia, and has naturalized across much of North America. You may have driven past it on a highway median last spring and mistaken it for wild mustard. The leaves are the source of the dye. The pigment inside those leaves is chemically identical to the indigo molecule produced by tropical indigo plants. Not similar, identical. The same compound, the same blue, produced by a weed that grows in roadside gravel. The difference is concentration. Woad produces less pigment per pound of leaf than tropical indigo, but it grows in climates where tropical indigo cannot survive, and the color it produces is among the most permanent dyes known to science. Laboratory testing rates woad-derived indigo at a light fastness of 8, on a scale where 8 is the maximum possible score. That means the blue does not fade, not in sunlight, not after washing, not after years of use. Neolithic farmers were growing this plant more than 6,000 years ago. Seeds have been found in archaeological sites across France and Germany. In the 1500s, the woad trade made the city of Toulouse in southern France one of the wealthiest cities in all of Europe. Merchant families built mansions that still stand today, paid for entirely by blue dye from a plant that grows like a weed. Plant it once, let it set seed, it comes back on its own every year without asking. The red. The plant is called madder, Rubia tinctorum. It is a perennial with long, scrambling stems and roots that can grow over a meter deep into the soil. Those roots are where the magic lives. The pigment is called alizarin, and it belongs to a class of compounds called anthraquinones, and it bonds to textile fiber with a permanence that synthetic dyes struggle to match. Madder red does not wash out, it does not fade in the way synthetic reds do. It deepens with age. The famous Turkish red, developed by dyers in Anatolia over centuries, was the most coveted textile color in the ancient world. European merchants spent fortunes trying to learn the technique. The secret was a multi-step process involving the root, a mineral mordant, and careful temperature control. Madder-dyed cloth from Mohenjo-Daro survived 5,000 years underground. Tutankhamun was buried wearing it, Roman soldiers marched in it, British redcoats bled in it. The plant grows in temperate climates across Europe, Asia, and North Africa. You plant the roots once. They spread through underground runners. After 2 years, you begin harvesting and the colony expands every season. More root, more red, more dye. No factory required. The yellow. The plant is goldenrod, solidago. If you live in North America, you already know this plant. You have seen it blooming along every highway shoulder, every abandoned lot, every untended fence line from August through October. Bright yellow flower clusters on tall stems. Most people assume it causes their allergies. It does not. That is ragweed, which blooms at the same time. Goldenrod is insect-pollinated. Its pollen is too heavy to travel on wind. What goldenrod does carry in those yellow flowers is a set of flavonoid pigments, quercetin, camphorol, luteolin. Together they produce a warm, rich yellow that bonds permanently to natural fiber when used with a simple mineral mordant. Light fastness tests show no visible color loss after 8 weeks of direct sun exposure. Change the mordant from alum to iron, and the yellow shifts to sage green or deep olive. Overdye the yellow with woad blue, and you get a permanent green. 3 colors from one plant. Over 100 species of goldenrod exist. Most are native to North America. Many have become invasive across Eastern Europe and Asia. They are so aggressive that governments spend money trying to eradicate them. They are spending money to destroy a dye plant that produces permanent color for free. The process for using any of these 3 plants follows the same basic principle. First, you prepare the fabric with a mordant. Mordant comes from the Latin word mordere, meaning to bite. It is a metallic salt, most commonly alum, that creates a chemical bridge between the dye molecule and the fiber. Alum is aluminum potassium sulfate. You can buy it at a grocery store in the spice aisle, dissolve it in hot water, soak your fabric for a few hours. That is the preparation. No special equipment, no protective gear, just a pot, a spoon, and a bit of patience. For blue, you harvest woad leaves and ferment them in an alkaline solution. The traditional method uses stale urine or wood ash water. Modern dyers use soda ash. Fermentation converts the precursor chemicals in the leaves into the indigo molecule, Dip the fabric in the vat, pull it out, watch it turn from yellow-green to deep blue as the indigo oxidizes in the air. That transformation from pale to vivid in 60 seconds is why woad dyeing has fascinated humans for thousands of years. For red, you chop dried madder roots into small pieces. Simmer them in water at a temperature below 70 degrees Celsius. Too much heat destroys the red and shifts it toward brown. Keep it low and slow. Add your mordanted fabric. Let it soak overnight. Pull it out the next morning. Rinse in cold water. The red is set. It will not leave. For yellow, you simmer fresh or dried goldenrod flowers in water for about an hour. Strain out the plant material. Add your mordanted fabric. Heat gently. The yellow transfers within minutes. Rinse and dry. That is it. One pot, one mineral salt that costs pennies. One plant that grows itself. Permanent color. A plant that dyes fabric permanently generates zero recurring revenue. Zero recurring revenue attracts zero corporate investment. Zero corporate investment means zero marketing budget. And zero marketing means 3 generations of people grow up without ever learning that the most permanent dyes on Earth grow in the ditch behind their house. This is not conspiracy. This is economics. The synthetic dye industry depends on chemical sales, on factory production, on supply chain complexity, on dyes that fade so that fabric must be re-dyed or replaced. A weed that colors fabric forever and spreads on its own threatens every link in that chain. So the weeds were reclassified. No longer dye plants, now invasive species. Something to mow, something to spray, something to eradicate. Governments publish management guides on how to kill goldenrod populations, herbicide recommendations, mechanical removal, controlled burns. They are spending money to destroy plants that produce permanent color, while the industry that replaced them pumps 280,000 tons of toxic waste into rivers every year. Meanwhile, a quiet movement is growing. Small dyers and fiber artists in places like rural Vermont, the Scottish Highlands, and southern Japan are bringing these plants back. They are growing woad in raised beds. They are cultivating madder along fence rows. They are harvesting goldenrod from meadows every autumn. They are teaching workshops and sharing their results. The colors they produce are extraordinary, and they are proving that what worked for 5,000 years still works today. The goldenrod is blooming right now somewhere within a mile of wherever you are sitting. The madder root could be growing in your garden by next spring. The woad would come back every year without you lifting a finger. 3 plants, 3 primary colors, every shade the human eye can see. No chemicals, no factories, no supply chain, no pollution, no cost after the first season. The only question is whether you will use them. Oh, and if longevity fascinates you, my friend runs a channel called The Centenarian's Garden. It is all about blue zone secrets and what actually helps people live past 100. Go check them out, you will not regret it.